VC ups. We're ready to start here.
Yep, go ahead and start. It's been recording.
Okay, great. So, welcome everybody. This is a small NASA Ames SETI Institute talk we have here today. Chris McKay pinged me over email a couple of weeks ago regarding this topic, and I think it's worth the while. So I'm going to let Chris introduce Dale Andersen, who, by the way, is one of the oldest bloggers on the internet. You'll hear about that. Give a warm welcome to both of them.
Thanks, Boris. As Boris said, I'm at Ames, just across the creek. You guys are engulfing us. You may have noticed that. And we're involved in planetary science, exploring other worlds. And one of the ways we do that is exploring places on Earth that are analogs. And Dale has been one of the leaders in that, in particular the application to Antarctica and diving in lakes, ice-covered lakes in Antarctica, and he'll talk about how that connects. We use a variety of Google tools in what we do and mapping out what we're doing and doing our research. And Boris and I have had a long-standing interaction on shared interests ranging from rovers to desert environments. And about 3 months ago, Boris pinged me and said, "What are you guys doing in Antarctica?" So that was the genesis of this. Dale is actually located in New York. He's here for a week, and so this was an opportunity to come and sort of talk a little bit about what we're doing. So, Dale?
Thanks, Chris. Thanks, Boris. Boris, I'll probably need a little help getting this going again. So we need to connect this window back up, right?
Yeah.
So back up here to screen share.
Screen share
desktop.
Yeah. That's the way we see the slides. Great.
Okay, where's the application again? Okay, we're good to go? Okay, great. Well, thanks everybody for showing up. I appreciate it. And what I want to do is, just by quick introduction, I am Dale Andersen. I work over at the SETI Institute with the Carl Sagan Center. And I do look at life in extreme environments, and I'll take you on a journey to see some of those areas. Again, basically at the SETI Institute, we're interested in the field of astrobiology and these major questions of, how did we get here and where are we going, and are we alone? Are there microbial ecosystems out in the universe besides the ones that we find on Earth, or even perhaps intelligent life that we can hear through the radio signals or other means? And then we have quite a few people that work in a whole slew of different areas. It's a very multidisciplinary approach to understanding the origins, evolution, and distribution of life in the universe. So we're interested in following the birth of the biogenic elements in the stars all the way up through the evolution of advanced life. And so we have to have knowledge of both things out in space, and in particular we need to have those lessons that we learn here on Earth. And of course, for us right now, since we're not going to be able to get out into the solar system or beyond the solar system anytime soon, we're most interested in trying to find life here in our own neighborhood, places like Mars, and some of the outer moons or outer planetary moons like Europa, Enceladus, and Titan. So a little bit about me and how I got to where I am. I've been working in remote environments like this since I was 22, and that was back in 1978, so I've been doing this for a pretty good while. I've got about 17 seasons in Antarctica, 60 plus months camped out in these areas over my life, another 30 field seasons or so up north with another 30 months up there. So I've spent a lot of time sleeping in the rocks and have gotten pretty comfortable at it and really enjoyed doing that kind of work. And I've been able over the years to help develop a lot of the techniques that we use to work in these environments, particularly the diving under the thick ice and putting the methods together for studying those environments. And that's what I'm going to talk about a little bit today. Let's see. So I can't really point to this very easily, can I? No. Okay. So here's the map of Antarctica, and we're going to go to basically two different areas. I've had the privilege of working in three major areas of the Antarctic. Down in the bottom part of the screen, you'll see McMurdo Sound, and that's where the U.S. Antarctic program and the New Zealand programs have their biggest research programs going right around Ross Island and the Mcmurdo Dry Valleys. Also, I've worked over in the Bunger Hills, which is over on the right-hand side of the screen. This is another ice-free area. Back in 1991-92, I was part of a joint expedition between the Soviet space program and the U.S. space program. We spent about 6.5, 7 months traversing around the Antarctic continent by icebreaker, and then getting dropped off in the Bunger Hills for 4.5 months to do it was almost like a Mars simulation. Have an international group of researchers, mostly Russian and American, one Canadian, live together and work together and get over those cultural difficulties and language barriers, just as you would if you were on Mars for a period of about 3 years during that kind of a trip. So this was a great expedition to do exobiology work with our Soviet counterparts. More recently, I've started working with Chris and Alfonso up in the top of the part of the screen. You'll see where it says the arrow's going up to Lake Untersee. This is down below South Africa. There's an area there called the Stromatolite oasis, and then you go further inland and you'll hit some mountains, and this is where the lake that we're studying is located. But I'm going to start this off in the Mcmurdo Dry Valleys. This is down in the Ross Island region, south of New Zealand, and this is where I cut my teeth in the Antarctic back in 1978, starting as an undergrad. There was a well, let me just back this up. So the Mcmurdo Dry Valleys are the largest ice-free area in the Antarctic continent. It's about only about 1% of the continent is actually ice-free, so it's a very rare type of environment. It's a very cold, dry place, and it's probably the best terrestrial analog that we have on the planet to Mars. And that's one of the things that has drawn researchers there, even from the early 1960s. JPL and Ames both had researchers going down there to prepare for the Viking program, for example. These were cold deserts that they wanted to understand how to look for microbiology at the time. So if you look very closely in these valleys, you'll see next to the glaciers, you'll see some ice-covered bodies, and those are small lakes in the valleys, and that's where we're going to be doing some of our work in a little while. Back in 1977, George Simmons, who's standing above me while I'm getting ready to jump into Lake Bonny here, asked this very interesting and important question when he got out to these lakes. Traditionally, people had only drilled small holes through the thick ice covers because the ice covers are anywhere from 3.5 to 6 meters thick. So that's a lot of ice that you have to go through to get to the water. Traditionally, people had drilled holes through those with a small jiffy drill, which is a 20-centimeter, 10-inch bit to get through. But nobody ever looked at the bottom of the lake. So most of the work was done in the water columns, looking at the phytoplankton and things are growing in the water. But nobody actually asked the question, what's growing on the bottom? And most people thought probably nothing. You'll probably just find rocks because light is going to be a limiter. The light has to penetrate through the ice and go down to the bottom to support photosynthesis. And most people thought that the light levels were just going to be simply too low. Simmons asked that question, and it's funny because back in those days, we didn't have cameras the size of my thumb like we do now that we could just drop down that little jiffy drill hole. It was easier to take a student or somebody like George or myself and drop us down a bigger hole, and that's what we did. So this is going to be a little bit about that story, how we got out there and how we started working in those lakes. And the biggest single problem that we faced that first year was how do you get through 6 meters of ice to study those ecosystems. Now out in McMurdo Sound, people had been diving in the ocean there for years and years and years. And this is actually my favorite place on the planet to go swimming. The Antarctic Ocean is just stunningly beautiful underwater. And I've had the opportunity to spend quite a bit of time under the ice in McMurdo Sound, and I would be there right now doing it if I could. It's just that great of a place. It's easy to make a dive hole in McMurdo. You just take a big track vehicle out to where you want to put the hole, and this hydraulic drill just pops up, and it's got a 1 meter diameter or 1.5 meter diameter bit on it, and you just pop it over and take off. And about a half hour later, you've got a hole drilled, and then you just clear the ice out. And then you can even pull a little hut over the top with a heater inside, and you've got this nice house that you can sit in, get all your dive gear on and everything, and then go swimming. The only thing you have to do is share the dive hole occasionally with seals. And of course, that's one of those things that you have to be careful about because there's not a lot of room in a dive hole, and if you got to get out and the seal's there, that can be a problem. But it is an incredibly gorgeous place underwater. I just thoroughly love it. It's filled with life, and the lighting is just beautiful, and there's ice, anchor ice all over the bottom. There's frazzle ice underneath the sea ice itself. It's one of those things that if you get to watch some of the videos that are online and on BBC right now, you should definitely do it if you can. Now, back in the early 90s, we had a Telepresence Rover that we were using. We actually had this rover connected back to NASA Ames by satellite so that we could control it through Ames, so they could make virtual dives with me. So Butler Hine and several others, Michael Sims over at Ames, would actually go swimming with me while they were in their office, and I would be 11,000, 12,000 miles underwater, or away underwater underneath the ice. And we also had the opportunity to turn that episode into an EPO opportunity. And we had students in California, Hawaii, and Virginia also drive this vehicle and take virtual dives with me as well. So this was in November of 1993, and at that time I was actually pulling together a little program called Dale's Dive Diary, and we were pumping this up through Quest here at NASA Ames onto the very, very new web at the time. So we've been kind of actively involved with trying to blog and get our stories out since the first time that we could actually do it. And this was actually the first time any broadcast like this had been made from the Antarctic. So we're going to go into the dry valleys now. This is Taylor Valley. You're looking at Lake Bonny here, and that's the Taylor Glacier at the bottom part of the screen. And that's looking out towards Ross Island. In the very, very background, you can see the volcano popping up as the island forms around where Mcmurdo's at. This is a typical campsite for us. This is where Alfonso, Chris, and I stayed a few years ago in 2009, 2010 in Pierce Valley. And again, it's one of the most Mars-like environments on the planet. It's a very, very dry, cold desert. And just off to the left, there's a lake. And this is the surface of that lake. This is Lake Joyce. And it has about 6 meters of ice on top of it. It's a very rugged surface. And we kept our camp up on the top, but we kept a working camp down on the ice. And here you can see a dive hut to the left and a science tent on the right. And the tripod is right where the dive hole is. But first we have to make some small holes, and this is how we make those small Jiffy drill holes. And this is the same thing that people would use for fishing, ice fishing in standard temperate lakes during the wintertime. But we end up with a lot more bit on the top of it. And so that makes it pretty easy getting in those small holes, but then that came to the problem of, okay, how do you make a bigger hole? And traditionally chainsaws had been used to cut out ice, but you can't do that through 6 meters, which is 20 feet of ice. You'd have to start the hole out really, really wide and then work your way down to the bottom. Finally, somebody would have to get down to the bottom and chop that piece out, and that just didn't seem like a very good idea. And it'd have to be moving a lot of ice to do that. So we came up with a pretty elegant solution. We took some copper tubing and formed it into a coil, like a hot plate, like you see. Or actually, I'll show you that in a second, but we use a steam cleaner to heat the water up and circulate it. This is a standard off-the-shelf Hotzi steam cleaner. You can see it's been modified a little bit. The hooks and everything on it are so we can transport it by helicopter. But then we have a coil that we just pass that hot fluid through. We lay that down onto the ice and let it melt. And we have a little pump on there to pump some of the water off so that we keep most of that heat being driven straight into the ice as it's going down. Now sometimes we can't use the copper coil, so we have to use a long cylinder. And here we just drill a Jiffy drill hole all the way through the ice, and we lower this copper tubing that you see here down just below the ice level, and then as it heats up, it convects the heat upward, and it enlarges that Jiffy drill hole over time, and it just gets bigger and bigger and bigger. There's pluses and minuses to using both ways. The nice thing about using the flat coil is you've got a dry hole, and you can go down into the ice as it's melting, which is pretty phenomenal. When you're sitting down into when you take a trip down into that ice it's usually about 10 years for it to form at the bottom and sublimate off the top and turn over. So it's a nice 10-year-old voyage back in time through the ice cover, and you can do the stratigraphy, you can take samples, and it's a great place to finally just catch up on the news. This is kind of a slow time for the work. You're just sitting there watching and babysitting the melter. Or if it gets cold outside and the wind starts blowing, you can actually get down in the hole and get on the copper coil and just enjoy the warmth, which is kind of nice. But eventually, you have to get in the water. Now, this is going back to 1978, and this was at a time when we were still trying to figure a lot of these things out, and a lot of the technology for diving hadn't caught up to where it is today. So we were still using wetsuits at the time. This was in November, and Taylor Valley at Lake Hoare, the outside temperatures were probably -15 or -20. It was probably a windy day, like normal, and we had just a couple of small tents. The tent on the right was a tent that we were sleeping in, eating in, and diving out of. And of course, we would have to walk out onto the ice over to the dive hole after we were outside, taking all of our clothes off and getting into these really thick wetsuits, which was not easy. Actually, getting into the wetsuits and diving wasn't so bad. It was actually getting out of the dive hole, getting out onto the surface in -20, and then having the suit freeze up, and then having to take it off. That was actually the problem with the diving at that point. So here you can see me as a youngster. I was 22 years old when I started this, and we were using double hose regulators, which people don't tend to see very often anymore. We were still using some old buoyancy compensators and some standard masts and things. And of course we're tethered. We've got a nylon line tied to us, and we were on rope signals. That's one important thing, safety element here, is when you dive in these lakes you have to be tethered or you don't get back to the hole. But this is how we changed things. A couple of years later, Doc Simmons finally got some money, and we bought some dry suits. And these were really quite nice to have. These were Poseidon unisuits at the time. And we also went over to full face masks. These are Kirby Morgan KMB-10 full face masks that have communications inside. And we wear them in sort of a bailout mode most of the time those years, where we had a tank attached to our back and we just breathed in like regular scuba. And here you can see me getting pulled out, kind of in that configuration. Now this is a leap of another 10 years. This is in the early 90s, and we started switching over to newer face masks that are lighter weight. And I'm still using the same mask actually. It's an XO26 by DSI, and we've moved over to probably more comfortable and easier to use dry suits like the Dewey suits that are available now. This is a CF200 suit that I've got on, a pair of Twin 70s for tanks, and again you can see a communication line coming down to me, which is also my guide to get in and out of the water and allows me to communicate to the surface. In recent years, probably one of the best things that's happened is now we have these dry gloves, and the dry gloves really make our ability to function underwater a lot nicer, because that's still the one thing that we can't really control very well is losing heat from our hands. Most of the time in the dry suits, all the way back, even in the wetsuits, back to the late 70s, I was never really cold underwater, but your hands would get cold, especially when we had the wet mitts on. But the advent of the dry gloves, and now we've got heating systems that we can put into these things, and that really helps us out. And of course now we've got some very nice huts that we can use out on the ice or in the field. We can store our dive gear inside, dry everything, hang up our dive suits, make sure that they're bone dry, and keep our science equipment happy. And this is sort of our typical setup in the dry valleys right now. We use surface supplied air for our dives, and you can see the rack of tanks in the back, and in the box on the right we have an air compressor. And then we open up this yellow box, and it's our gas management system and a comm box. So this is where the tender would be standing, or a dive supervisor would be standing to communicate with the diver underwater to help with safety issues and also to record the science that's going on. And then we have a tether. And these tethers, in this case, it's a tether that allows the air to flow back and forth on surface supplied, and they're usually between 70 meters or a little bit more, maybe 100 meters, depending on the tether. But when you're that far out, it's a pretty long ways. If you're a football field length out on a line under the ice, when you're that far away, you've got to ask yourself, can I swim back on one breath? And usually that answer is no. So it gives you pause for thought when you're that far out. So what I'm going to do now, so that's sort of the history of where we've gone over the years in the dry valleys. But I want to shift gears a little bit and go into a little more detail about some of the work that we're doing in Lake Untersee. And this is pretty cool work that we started up in 2008 with a very different model for doing the research. And this is our dive logo from last year. In fact, here's our research team from this last season, and Alfonso, who's here in the audience with us, is standing next to me on the right-hand side there. And it's a fairly international team. We have normally about 6 people or so that go down with us. I like to keep the field teams small. It's nice to be able to pick from a known pool of people. So we've worked with people over the years, and we know who's reliable in the field, who's reliable with their skills, if they're a diver, or if they're a climber, or if they're good at one particular set of skills. It's nice to be able to count on them for doing that. And again, it's very international. This last few seasons, we've had people from Russia, Austria, New Zealand, Canada, and this next season we'll probably, or if we're lucky, have some people from Japan coming with us. The selection of people and individuals really is dependent on the kind of science that we're doing at any given time. But I really prefer to have individuals that we've worked with before, or have had people that have worked with us, that have had other experiences with other people that we know, so that we can understand how they're going to operate in the field. And sort of the additional things that we look for, so in addition to your science skills, we're looking for people that have a multi-dimensional capability to them. So we want them to have other tools in their toolkit. They've got to be skilled at doing a diverse set of things, like being able to dive or being able to climb, understanding how to operate in cold conditions, and understanding how to work in those conditions. And those are all things that you don't come to just naturally. It's something that takes time and effort to learn. And learning how to operate in these environments safely and being able to count on one another is something that's really paramount to us. And so I want people that can work in a group or work individually. If we've got a little problem, we want to be able to set somebody off and just say, go puzzle this out and figure it out. Don't bother us for a while, just get it done. And you expect that to happen. We want people that knows when it's time to talk and when it's time to listen. When it's time to lead and when it's time to follow. And those are also very important skill sets that are applicable in everyday life, but they're really, really important for us out in the field. And it's really important to have a person that knows how to tie the right knot at the right time, which kind of sums it up. So our journey to Lake Untersee starts in Cape Town, South Africa. That's where the team assembles, and we all board in Anuchin 76. And this is an interesting project in that, unlike the work that we do in the Mcmurdo Dry Valleys, where we're typically supported through NASA or the National Science Foundation and participate in the U.S. Antarctic program, in this case we're totally privately funded, but we're also embedded in the Russian Antarctic program. So it's an interesting mix of how we go about the funding process and getting down there to do the work. ALCI is a company that formed from some of the people that arrived in that area after the breakup of the Soviet Union, and decided that their skill set was that they knew how to do logistics in polar regions. And so they set up the company ALCI to provide logistics in the Queen Maud Land region, and they service now as a nonprofit company the Drumland community, which is about 13 countries. And then also there's another side of their company that deals with some of the tourism that's picked up. But we jump inside this aircraft, and it's about a 6-hour flight to get down to Novo Station. We land on a prepared ice runway, and this is actually a pretty good piece of technology to be able to build a runway that's safe to land on in these kind of environments, and the Russians have been doing it for a very long time, and they're very good at that. And again, ALCI's ice runway is the hub for Queen Maud Land for many countries, like the UK, Japan, Belgium, South Africa, of course Russia, and a number of others. Our first piece of business to do is to actually unload the aircraft. That's part of our deal. As soon as the plane lands, we don't walk off to some little hut to go get coffee. We walk to the back of the jet and start unloading the entire aircraft, and in particular to look for the stuff that you brought down and pile it up and get it over to where it's supposed to go. And again, we're guests at Novolazarevatsky station, the Russian station at Schermacher Oasis, which has been there operationally since about IGY. I think it was built in 1960 or 61. And again, the environment of the Antarctic, so it's always cold, and unlike what you typically think, sometimes it's not brutally cold. Sometimes our temperatures are not in the -40s and -50s. In fact, most of the time that we're there, we're in the summertime, and the temperatures are typically cold when we first get there. And in this case, Lake Untersee and Schermacher Oasis is fairly north in terms of the Antarctic. And our mean annual temperature in this area is about -10. So we see -10s and -15 Cs while we're there. And then the temperatures creep up towards freezing during the summer months. Light, it's usually, by the time we get there, it's light 24 hours a day. So we do have to worry about that and how it affects our working cycle. And that's very important for us to try to stay on track so we won't start drifting. You don't want individuals on your team drifting off in different time schedules so all of a sudden everybody's waking up at different times. So that's another important part of the work that we do. Medical care, we have to understand where we can get some medical care, we can get some at Novo Station, but for the diving aspects of this, our nearest recompression chamber is in South Africa, which is a 6-7 hour flight away, one way. So a jet would have to come down, take us back, and then of course we would have to get in from the mountains of Queen Maud Land into the ice runway to get on that jet again. So it's not it's a non-trivial process if we have a problem. And then the same hazards that you'd typically expect, falling through crevasses, getting stuck in really bad weather outside in storms. And then we have the physical isolation. Once we're put out into our field site, the 6 of us are pretty much on our own. We don't have any contact other than calling into the Novo Station a couple times a day to let them know that we're okay. Otherwise, we're totally apart from everybody. We're isolated and we don't have contact with anybody other than through a low bandwidth iridium phone. But before we go out there, we have to assemble all of our gear. So we have some gear that we've stored down there. We have tents and we've got sleeping bags and snowmobiles and things. And we spend a couple of days getting organized and pulling all this gear together and preparing it for transport. That's actually a pretty big effort. And as I get older and older, I find that recovery from having to do this kind of hard labor, because we're not actually scientists, I think we're just movers. We just move things from pole to pole. And it's always heavy things. But we end up taking this trip, and in the upper part of the screen you'll see Stromatolite Oasis, and that's about 30 kilometers long. And if you can see the little light blue line in there, that's actually our GPS track that goes across the ice and inland into the mountains over to Lake Untersee. And you'll see that line go down a glacier, and then it hits the lake that you can see down at the bottom right part of the screen. So that's our road to Lake Untersee. It takes about 6 to 8 hours to make that trip over the ice by snowmobile or by truck or track vehicle. And again, that depends on the weather and the conditions and the visibility. And this is where we're going. This is a satellite image map of Lake Untersee and Lake Oversee. You can see the Anuchin Glacier makes this really nice sloping road right down to the glacier, down to the lake's surface, which is quite nice for us because we can literally drive down that glacier right onto the lake ice. And that's the main place that we've been doing our work. In the upper right-hand side, you can see Lake Oversee, and this is where we were camped last year. We wanted to do a comparison with Lake Oversee to Lake Untersee, and we finally were able to get up to Oversee for a season to do that work this last year. This is another part of the work in this area, of course, is the whole history of working in the Antarctic. Because it's only been a very short period of time that people have actually been working down there. Since its discovery. It's only been within a couple of generations that these places have been worked and actually visited by people. So in this area, it was the Germans who discovered Stromatolite Oasis in the mountains in Queen Maud Land on the 3rd German Antarctic expedition back in 1938. It was during part of the buildup of the war effort for them, and they were actually trying to find areas that they could put in whaling stations, and so they could get whale oil to help with their industrial processes. And during that work, they came in and they found the mountains, and that was the first time that this lake was photographed. It was in 1938, 1939. It wasn't mapped really until the Soviets came back in during IGY, and then the Norwegians came in a little while later and started doing this more serious aerial photography of the area. But this lake wasn't visited by a person until 1969, which I think is kind of cool. Just same time that first time we went to the moon. So I've always thought that was kind of nice. And then more recently, there's been extensive work done by some of the Germans and Russians and others in the 80s, and we've kind of taken over the place for the last few years, going back off and on since 2008, and we've made 4 trips there since. What does SAE stand for? Yeah, SAE is the question was, what does the SAE stand for? And it's the Soviet Antarctic Expedition. So the SAE is Soviet and the RAE is Russian after it switched over in the early 90s. But this is where this site is located. These are some of the mountains that you find in this area of Queen Maud Land, and it's stunningly beautiful mountains. It's truly just magnificence defined, looking at these spires of rock coming up out of the ice like they do. And this is our trip. So we literally start going across this barren wasteland of blue ice and snow, and we do have to worry about crevasses as we're going out. In particular, there's several areas that are laden with crevasses, and it takes us several hours to get across those spots. And usually we end up pulling the trucks out a dozen or so times by the time we get out, and hopefully without breaking anything. Occasionally we break the wheels or things fall off and we have to put them back on. But here you can see one of the trucks has got a tire stuck, and the other truck has moved over in front of it and is using the winch to pull it back out. Now, oddly enough, last year we had this same scenario take place. The truck got stuck. Actually, I was in one truck and Alfonso was in the other. And so my truck got stuck, and Alfonso's truck pulled out in front of us and went around to come up in front to put the winch on, and they were pretty good ways away, and their truck got stuck. So we were just really fortunate enough that the winches from both trucks reached to one another, and we were able to pull each other out. Otherwise, it would have been a long day. But we also have to snowmobile out, so this is actually one of the funner parts of the trip for me, I think, is skidooing out into the mountains like this. And it's a really unique and intimate way to learn how to live in the cold and work in the cold, is when you ride skidoos in the Antarctic like this. But eventually we all get to the lake, the trucks arrive, they dump all of our gear off, and the trucks depart, and we have to set up our camp and start work. And this is really, really an important part of the trip, right at this very moment, because our support has left. You know, we're on our own, and now the first thing that we have to do is get shelter up very quickly, because this area is really prone to high winds. So we need to have at least one tent up. Usually takes us about 3 days to get the camp fully established. But if we don't get that first tent up, or 2 tents up, or as many as we can get up, depending on how tired we are and the timing of when we arrive, we could get nailed by really bad weather, and we'd be spending it out in the rocks instead of inside of a tent. But once the tent's established, you know, the camp's established, we have a pretty nice home, and that's where we live for the next 6 to 8 weeks. And again, it's just a really stunning backdrop. You know, the lake is completely ringed by these large mountains, and these mountains are all composed of anorthosite, which plays an important role in controlling some of the chemical features, for example, the lake water. But here it is. This is a true example of a land of rock and ice. This is the surface of Lake Untersee. So we've got 2.5 to 3.5 meters of ice on the lake, and we've also got probably several hundred boulders. Some of these boulders are larger than the snowmobiles, maybe 2-3 times as large as the snowmobile, that have worked their way out onto the ice and are floating on that ice surface. So it's not too often that you get to see floating boulders. This is our tent camp from last year. I just wanted to give you an example of sort of how we established the camp and why we put it up this way. And this is I took my personal drone down with me. DJI loaned me a Phantom to take down with me, so I've got a Phantom with a GoPro on it, and shot some aerials of our camp. And you can see that we've got a science tent in the back, we've got our cook tent and the dive tent, and then we've got some individual sleeping tents, a toilet tent, and then some sundry gear and some small generators. But this is our home, and this is how we establish it, and we work in and out of it like this. And again, it's important to maintain that schedule that we have. So we try to stay on schedule for breakfast in the mornings, kind of a lunch snack time whenever we want it, working around work, and then we have we try to come in for a dinner time, you know, around 6 o'clock or so. But it's really also very important that we have a place to retreat into. We keep heat on in a couple of these facilities, like the dive tent. We have to keep heat on to keep some of the dive gear dry. The science tent has to have heat so we can keep some of our equipment and our science samples from freezing at times. And then it's really important to keep the people from freezing too. So with the cook tent is another key place that we have to have heat that we can come into and get out of the cold from time to time. Now we do monitor the climate, and that's a very important part of our job. And it's both so we can monitor climate change in this area, but it's also so that we can understand how climate affects the lake ecosystem. These are physically driven ecosystems, and that ice cover is probably the key thing that impacts the ecosystem underneath it. And of course, that's all climately driven, how thick that ice is and how long it lasts. And this is the kind of weather that we do tend to see. And if we have time, I'll show you a quick video towards the end that'll demonstrate this a little bit more. But we do see pretty heavy winds from time to time. The temperatures wax and wane, you know, but our mean annual temperature in this area is, like I said, about -10 degrees C, so that's not so bad. It's really the winds that make the working there a little harder. So when it's really windy outside and it's cloudy, that's those difficult days for us to work outside. Now, it's interesting to compare this area with the Mcmurdo Dry Valleys. These are alpine lakes. Lake Untersee is at about 560 meters in altitude, and Lake Obersee is at about 800 meters. So they're alpine lakes. We're a little higher up. The Mcmurdo Dry Valleys are a little further south, towards the South Pole. We're a little further north at Lake Untersee. The Mcmurdo Dry Valleys, though, if you look at their hydrological cycle, it's really based on melt. So when the peak temperatures during the summers come up just above freezing, the glaciers tend to melt off. That liquid water drains down into the valleys and replenishes the water for the lakes. It seems pretty easy to imagine, and it's the way it works there. In the Untersee area, it's a little different. We don't see melt. The evaporation rates are so high that sublimation really is the dominant feature here. So we don't see melt running off the glacier. As a matter of fact, that's why we can actually drive down the glacier, because if the glacier was melting, we'd have these large melt channels in it. Otherwise, we have this nice smooth road coming down where the winds have ablated it off and kept it smooth. It's the same with the ice. It ablates very quickly off the surface. So we don't have any melt streams coming into these lakes. It's one of the quirky things that we noticed when we first arrived there, and other people had noticed. Where's the water come from? There's no melt streams that come in during the height of the summer. So it's obviously coming in from subglacial melt in the front of the glacier. The Anuchin Glacier is actually moving into this lake at a constant rate of several meters per year, and that water that comes in as ice melts and adds to the water of the lake. And then there's probably also subglacial melt coming from beneath the glacier as well. So it's a very different process, and it has a bigger impact on how this ecosystem operates. And you can see that this is sort of a cartoon cross-section of Lake Untersee. We've got the Anuchin Glacier over on the left. We have a deep basin that goes down to about 170 meters or so. We don't know the exact deepest point, but that's the deepest reported so far. Then it comes up a slope out in front of the peninsula where we camp and where we have our met station, and then it drops back down into another anoxic basin on the other side that drops to about 100 meters. And this is a really, really cool lake.
If the average temperature is below freezing, where does the heat source come that keeps the water liquid over long periods of time?
Right. So the question is what's the heat source for keeping the place liquid over time if the average temperature is minus 10? Well, it's the average temperature, not the peak temperature. So you do have peak temperatures coming up above freezing at times, but it's also solar heating. So it's all solar driven. So the sunlight is the big driver here. The ice cover actually traps the heat inside as well. So once you've got the ice cover there, as freeze-up takes place, the latent heat pushes back down in and keeps that heat budget going. So you'll never freeze it down solid unless it really gets cold for a long, long period of time. But the water, again, is very, very transparent, which comes back to driving that heat into the lake. And we see quite a bit of the light penetrating through the ice cover. We get around 5% in this lake ice to get through the ice. And then we can probably get some of that light down to at least 130 to 140 meters, or probably even deeper. We found microbial mats growing at a depth of 160 meters in this mat photosynthetically. It's an interesting lake also because the water pH is up high. It's 10.6, which is kind of unusual for some of these lakes. But what really sets this lake off apart from a lot of the other lakes is in that anaerobic basin down below about 80 meters, from 80 meters down to 100 meters, the methane levels just go crazy. And you get dissolved methane in this lake at 20 millimolar, which is very, very unusual. There's only a few places around the planet where you can get dissolved methane levels that high. There's some rift lakes in Africa, like Lake Kivu, that has that in that lake, and then also right on top of methane clathrates in the ocean. Right at that surface above the methane clathrates, you'd see values like that. So it's very unusual that you see this much methane production in a lake. And just as an example, if you took a 1 liter bottle down to the bottom, 100 meters, opened it up, filled it up with that water, and brought it to the surface, and opened it, you'd get about a half a liter of methane out of it. So it's a pretty substantial amount of gas. In fact, you could plumb it with a pipe, bring that pipe to the surface and then burn it if you wanted. Now, the whole volume of gas in there is not a huge amount, so you'd burn it out pretty quickly, which wouldn't be a cool thing to do for the lake, but interesting to think about. So this is our typical kind of a day. We have to drill holes, melt holes, saw the holes to get in to make them bigger, break the ice out to get a little bigger, and then jump into the water. So that's kind of the kind of work that we do, that once we get the holes opened up, then we can really start our work, whether it's with a sampling device, an instrument, or the divers doing some specific task. But here we are, this is Chris McKay and myself getting ready to continue through a hole that we've already been working on at Lake Untersee. We've got it down, the hole, we have to, every time we get down a little farther into the ice, we have to pull the thing out, add a bit to it, and put it back into it to keep extending the length of the drill bit. And here we are making the final push down through the ice. And again, sometimes you have to be very perseverant, and teamwork is a really important part of the deal here. So everybody's got to work together and know how to work with one another. So this is coming underneath the ice, and I just want to talk about the freeze-up part again. So another interesting part about this story with the gases is not just the methane being high, but all the other dissolved gases. The air group gases are very high as well. And so if you look at the underneath surface of the ice, you'll see these pockets, and these are gas pockets that have formed as freeze-up takes place underneath the ice. The gas molecules are too large to fit in the ice lattice, and they're pushed back into the water column. So it's sort of like a bicycle pump pumping up the gases in the lake. And eventually, the dissolved gases will nucleate and form bubbles just underneath the ice. And some of these bubbles get very, very large. And in particular in this lake, they get very large. They'll get tens of meters across. You'll get pools of gas up underneath the ice. And some of that gas will actually get entrained in the ice. And I'll show you the result of that here right now, I hope. This is actually at Lake Untersee with, let's see if you can hear this. Nope. Okay, well, this is at Lake Untersee last year. Alfonso and I went out to drill one of the holes, and we drilled down through it, and we knew we were going to get a little bit of water coming up, but we didn't realize we were going to get quite so much. This was actually enough water to blow the drill out of the hole. So we were holding on to it, and Alfonso finally asked me what to do, and we turned it off. The drill actually started reverse drilling as fast as it was going when it was turned on, just because the water pressure was pushing it up the other direction. And we finally let go, got the drill out. You know, we were standing inside this fountain of water probably for 10 minutes or so as we were trying to deal with the drill. And there's Alfonso for scale. This thing blew water like this and gas for, I don't know, another hour to 3 hours at that height, and then it kind of dribbled out over the next several days. So there's a huge pool of gas sitting right up underneath the ice here. That will get replenished again as soon as more gas comes into the lake, which there's a really good source of it. The Anuchin Glacier, of course, is glacial ice, and glacial ice has a lot of entrained bubbles in it, and that gas just basically gets delivered right into the lake. So it's like an air stone coming into the lake, essentially, adding that volume of gas to the lake every year. But then it's time to get into the water. So we keep a portable compressor out in the field with us, and then we fill up the tanks and get everything set, and then it's time to get in. So at Lake Untersee, we'll usually skidoo over to our dive site, get dressed out, and here I am sporting my new dry gloves, these Kubi rings, which are really quite nice. It's another one of these things, when you're diving, you're always trying to find the nicest thing that you can put on, the easiest thing that you can deal with, and so far the Kubi rings, which are really quite nice for me, have shown me that I can get in and out of those ring sets very easily, even when I'm cold. Sometimes you can get these dry glove rings on, but sometimes you can't get them off very easily, and these Kubis work quite nicely for that, and they don't leak. So then down we go. We head on down. Normally we dive only with one person under the ice at a time because it's more difficult to have two people in, especially if you have an accident or a problem, and you'd have to have both divers coming up out of the hole at once, and there's not very much room in the hole. So as long as we're on tether, as long as we've got good communications, and there's no obstructions underneath the water, we're pretty comfortable with diving by ourselves, and that's been the policy of our diving in the U.S. Antarctic program in these lakes now for the better part of 25 years or more, and it's worked out quite nicely. But on this occasion, I wanted to get some shots. Go ahead.
One question. You mentioned that you'd actually measure the depth of the lake. If you're doing tether diving, how are you getting down there?
Yeah, we don't go to that deep. So the divers, yeah, I'll get to that in a second, but the divers, the question is since we've measured the depths down to 170 meters and 100 meters in both the basins, do we get down that deep? And only instruments and sampling devices go down to those depths. The divers are 40 meters or above, so 130 feet is the deepest that we can go. And we dive very conservatively. Again, it comes back to if we have problems, like if we get bent or if we have an embolism, we're going to be in bad shape because we can go on to oxygen in the field and we can do some basic first aid, but it's a long trip to get back to South Africa.
And just you're on air, not nitrox.
Right. So the question is what gas do we use? We use air. Mostly, it's we don't really need any other advantage in terms of nitrox that would give us for time at depth. What we really need, what we just need is a very simple way to compress our air. And if we had nitrox, we'd have to mix the gas as well. So we don't want to have to do that. And for us, the cold is a bigger driver than, typically the diver will get cold before you'd run out of gas, unless we're really going down deep, and then nitrox doesn't make a difference anyway. So we're just on air. But in this case, I wanted to take some shots of a diver doing some work, so I got in with Ian one time. Ian went down to take some core samples, so that gave a little bit of perspective. Now this particular shot is the bottom of the lake at Lake Untersee, and there's two features here that really pop out very quickly. One, it's dominated on the bottom by these large conical stromatolites, and this is the first time this has ever been documented in a lake, and its relatives go back about 3.5 billion years in the fossil record. So it's a pretty unusual find for us, and it's a really exciting find. Now if you look up underneath the ice, way off in the distance, you can see one of those big gas bubbles I was talking about. That's a pool of gas that's probably 15 to 20 or 30 meters across, that's just waiting to get up into the ice and have us drill into it one of these years. But here's another example of these conical stromatolites, and it's really a world that we've never seen. So we've seen their fossil relatives in the ancient sediments of the Pilbara region, for example, in Western Australia. But we haven't seen modern examples, and this is the only place that we know of where these large conical stromatolites are forming in a modern setting. If you look at the coloration on them, you'll see that they're kind of that purplish hue, that nice pinkish purplish hue. And that's the phycoerythrin, which is the dominant pigment for their photosynthesis capability, and that's helping them to collect the light level, or the quality of light that's coming through the ice, the nice blue light that's coming down to them. It's tuned to that light level. And they're very, very efficient at what they do. They can use every little bit of sunshine that comes down through that ice to make a living. And we've got some of these same players that we've seen in a lot of the other lakes that we work in. Formidium and Leptolingia are the two big guys. And interestingly, there's no diatoms in these lakes. We don't still quite know why that is, whether it's something special in the chemistry that's keeping them from being there, or if it's just because they're geographically isolated and they haven't gotten there yet. But it's probably a combination of several things. But it also may we see diatoms in all the other Antarctic lakes that we've worked in. For the most part, there's a few pockets that there's reports of no diatoms. But all of those other lakes, none of them have these large conical stromatolites growing. So we think that may play a role into the morphologies that are developing in this particular lake. Maybe the absence of diatoms helps these cyanobacteria form the kinds of structures that they want versus what the diatoms help them make later.
The conical shapes are light.
So the modern stromatolites that we see are microbial mats. These are cyanobacterial mats that are actively forming these dome-shaped structures, and they're laminated inside, and I'll show you that here in a second. These are the same photosynthetic mats that we see at 160 meters, and you can see that they're that very rich pink phycoerythrin-rich color, and that's where the pigments those accessory pigments are helping them to harvest the light that's available, even those 1 or 2 little photons that are getting down to that depth. Now, if you take one of these conical stromatolites that we've got and you slice it in half, this is what you see. You can see that it's very laminated, and in the Mcmurdo Dry Valleys over the years, Ian Hawes and some others have finally figured out that most of what we see are annual layers. Layers like this are laid down every single year. Here, once we came back and we did some of the radiocarbon dating to see how old this thing was, the relative dates between just a few centimeters apart was upwards of 2,500 years. And so the math didn't work out for a yearly or an annual deposition, but it's more of a decadal scale. So it's taking a long time to build these things up. And that makes sense because there's very, very little sediment that we see in these waters. So these formations take a pretty long while to get to where they're at. Again, the question is, does it actually take 2,500 years to build this little tiny conical stromatolite that we've got here. Okay, here's just a couple of shots. So this is sort of, again, the typical work that we do that really does transport us back in time. Here's Ian taking those core samples, and you can see that they're little tiny plugs. Also, notice how gently Ian is on the bottom. So this is another really big part of the training that we have to do for working in these lakes. These lakes are very delicate, and we don't want to disturb the microbial mat systems very much. So you have to really understand how to control your buoyancy, and that's a real skill. It's actually a difficult skill to learn, and most people don't pick up on it very easily. But here you can see that the only thing that are touching are the tips of his fins on one side, and where his hand is picking up the core, and then you can see the core box over on the side. So we make sure that the areas that we disturb are really minimized by working hard to do that. Now again, if you went back in time 3.5 billion years ago, and Chris Alfonso and I did this a couple of years ago, we went over to Western Australia into the Pilbara region, and this is sort of a mecca for astrobiologists because this is one of the areas where you can go. It's one of the very few areas on the planet Earth today where the rocks haven't been folded back into the earth and put into the furnaces, so to speak, and had the records removed. It's one of the few places where you can go back and find sedimentary rocks that date back 3.5 billion years and find evidence of life in them. So what you're looking at here is some conical stromatolites that are preserved in that record. The one on the top is about 1.8 billion years old, and then the two over on the right are 3.5 billion years almost over in an area that we visited. So those are actually outcrops in the rock that we saw and photographed at the time. And you can see the three-dimensional cones in the lower one, the lower right, are a great matchup for the conical stromatolites that we have in the lake. So what I'm going to do is I'm going to just really briefly go through a few tools of the trade that we've got, just so you can see some of the things that we work with, and then I'll be wrapping it up here pretty quickly. But this is the typical stuff that we use. We'll take sediment cores, we have light meters, oxygen and pH meters, conductivity, temperature, depth meters. We use fluorometers to help us understand how the microbial mats are able to photosynthesize under the conditions that they're in. And then we have these underwater microsensors that allow us to check for pH and oxygen levels down inside the mats at a very, very high resolution scale. And then of course we've got cameras, and the Lidar system is actually a unit that we've used once to paint the bottom, and it gives us a three-dimensional image of the bottom of the lake. And these are some of the things that we take down. So this is the PAM fluorometer that we take down. And again, you have to come down and place these things into a certain position without tearing the place apart and actually tearing apart the study site that you're trying to study. And it's difficult to do that. It looks like it's easy, but it's not, because you're on a tether, you've got big weights on your belt, you're carrying equipment with you, you've got the buoyancy control issues. So it's a real skill set to get these things down and put them in place properly. This is the microelectrode system, and what you see here is a box over on the side that will record the data and take the measurements, and then over on the left-hand side you see the microelectrode that's been attached to a stage micrometer. And we can actually push this little fine needle, it's like this, at the very end it's thinner than a human hair, down into the microbial mats at a 0.5 micron increment. And this is actually the coldest work that we do, because as a diver you sit down at the bottom and all you do is move your fingers very slowly over a period of anywhere from 30 minutes to an hour. And that's where your hands just really get pretty cold. And that's why the new electrically heated gloves are probably going to be a real help for this kind of work in the future. We do have, this is an example of the Lidar, so you'll notice here that we've got a lift bag on it. So when we use tools like this, actually this is the same version of that little microelectrode system, but it's an automated system. But it's large enough that we have to use a lift bag to pull it over into the spot that we want it, gently lower it down, and then use it from the surface. It's really nice to do it that way from the surface, but it's also difficult getting the thing in place. So there's trade-offs on using this kind of technology as well. There's the Lidar system. It's a large item that we have to take down with a lift bag and put in place gently, and then it paints the area with a green laser and gives us that three-dimensional map of those microbial mats on the bottom. And then there's this very simple stuff. This is just plexiglass tubes, and these are things that we stick down into the dirt to collect samples. And there we go, back to home. But after we're done with the dives, then we have to take the samples back, and we have to take them back into the lab and process them. So there's quite a bit of work left afterwards. And that's sort of the end of the day for us, is coming in and finishing up the samples and then checking on the camp and then going back into dinner and getting ready for bed. So what I want to do right now is just show a quick video, And I don't know if there's audio on here or not, but we'll see. And this will kind of sum up a little bit of what we've been seeing. And there's no audio. That's a good idea. And this is just a panorama around a little bit of the area. And just briefly, this is an example of a little bit of. This is just an example of some of the weather that we see. So this is not a too bad day. This is actually with winds that are only about 45 or 50 knots. When they're blowing at close to 100 knots, that's when we have to really be a little more careful. And we have measured winds at creeping up to 50 meters per second, which is around 112 miles an hour. We have lost tents in the field. Sometimes the winds come down and they're just like bowling balls hitting the tent, and they'll just flatten one tent. You know, so like 2 years ago, I was sitting in my tent, and a couple minutes later, the tent was sitting on me. So we do have to keep extra tents outside, and during these times, you can't be actually inside the tent most of the time. Quite often, you have to be outside looking at everything to make sure the tents don't blow away. So again, it's nice to be in a comfortable tent when it's in a storm. On the other hand, you don't want your gear to blow away, and you don't want your tents to blow away, so it's time to be outside looking to make sure that it's all safe and sound. This is just sort of the typical scenario of getting dressed out at the dive hole and jumping in. You can see we're putting on the weights. I think that's actually Alfonso in the back helping me out. And just getting suited up and going. And then it's down through the ice. And down to the bottom. Yeah, it kind of varies where it is. Depends on sort of the part of the season that you're in. But sometimes you can get a freeboard that's, what, 30 centimeters or so, Chris? Yeah. So it can actually be a fair... that's one of the reasons we take chainsaws out and chainsaw around the hole sometimes to get the diver down closer to the lip of the water to get in and out. It makes getting in and out a little easier. But these are the microbial mats that we see, and they're just gorgeous. Again, this is the only place on the planet that we know of where these large conical stromatolites are forming like this. And these are all about anywhere from a few centimeters to a half a meter tall. So some of these things are, you know, almost this tall underwater, which is pretty unusual. Most of the things that you see in most environments are the size of your finger or a little bit bigger, maybe the size of your hand. So this is a pretty unique system. And I'll just stop it there.
Do you have any idea what's happening in the lake during the winter, or how things change during the winter, or do you have any plans to find out?
Yeah, so the question is do we know what's going on in the winter, and do we have any plans of trying to find out what's going on in the winter? Go ahead. Oh, you can throw it on us.
Yeah, I'm gonna.
Oh, sorry. Okay. Well, we do some of that. So the biggest thing that we've got that's out there full time is the Met Station. So the climate station has been out there now for 5 years, and we've got a really nice long 5-year data set. Matter of fact, Chris and I have been working. That's the reason I came out here, was to work on that data set with Chris to publish a paper for it. So that's the most important thing that we leave right now. There are some underwater sensors and some devices that we'd like to leave underwater, but we haven't pulled that off yet. You know, so that might be in the future. It's a little more difficult to do that, and of course we have to ensure that we get back every year or every so often to get the data, and that's another part of the story too, is, you know, maintaining funding and trying to get the funding to keep us going, and to get those tools to leave underwater.
How long does it take to that drove a hole with a coil. Can you show us some information about that?
Yeah, so how long does it take to make a dive hole with one of the coils? Well, the flat coil, again, it depends on how thick the ice is. You know, if it's 2.5 meters versus 6 meters, it'll obviously be a big difference. But in general, we can count on a day or two, or maybe up to 3 days to make a hole. By the time we get it all set up, then we open it up and water floods and comes up to the surface and the hole's ready. You know, so it's a couple of days at least. It is. It's a real concern of ours, and we try to be. It's like anything, you know. People, anytime you study anything, you're going to change the environment a little bit. So you try to minimize that change. And one thing that we do is, just for example, everything that we bring into the field with us, everything goes back out. So all of our waste goes back out. We collect all the human waste, all the gray water that we produce, all the trash, everything that goes in and out with us. For working in the lake itself. Over the years in the Mcmurdo Dry Valleys, we've wrestled with this problem as well and have come up with suggestions and techniques that help minimize that as well. And part of that is keeping the gear extremely clean to make sure that we don't transfer organisms from system to system, for example. But our impact is really pretty minimal to these lakes. You know, our scale is so much smaller than the volume of the water that we're working in. And again, we try to minimize anything that we do that would disrupt anything.
So you have to reopen the holes every year? They say close up, or?
Yeah, they'll close up over a period of weeks to months. They'll freeze shut again. So every year we have to open up a hole. And if depends on when you're there. If you're working in the dry valleys, for example, in October or November, a few days can pass, and you'll have to go back out and chip the hole out or chainsaw it out, you know, depending on how long you've left it. But after a week, you can count on pretty thick ice being back in the hole.
Oh, great. That's all the questions. Please join me in thanking Ken.